All right, um, so this is the pretty much the what we wanted to get from linear algebra. Okay. Um, Classification of linear operators according to their eigenvalues, and so implicitly it is the real ones, and so that's the limitation of what we got. The behavior that is a simplified behavior in particular directions. Okay, so if those particular directions are different, for two different eigenvalues, remember we have a quadratic equation. Our characteristic equation is quadratic. We expect it to have two answers, two roots. If they're distinct, and that is, remember that picture, like this and like that and like that. So this is the edge case when you have one answer. So it's the more typically you have none or you have two. So you have two, meaning that they're distinct, which means that there are two different eigenvalues. Say lambda one, lambda two. Okay, and then it is once again. So it's if and then what if the eigenvectors that they or their eigenspaces are also different? Okay, so these are not different, not equal, and then in which case that's where we are. That's the ideal case. So the other two are so far excluded, these two, and then let's see what if that's the case. It is a generic case, even though kind of half of the whole possibilities. And in that case, these two particular directions, the eigenspaces, are the directions in which everything is very simple, and therefore our behavior, meaning simply is the stretch of the vector. Later on, our differential equation will also be easily solvable in that direction. We had examples of that. Okay, and then so then the way it works out. So back to linear algebra, these are the two directions. I call them v1, v2, which are basically nothing but the vectors among infinitely many that point in those directions. Okay, so as the straight lines, and then they are there's direction vector into the many, and then suppose that we have them. Okay, so if that's the case, the behavior is this right here. So the linear operators simply multiply by lambda, and these vectors as well as all the multiples are nothing but what happens to them is to stretch. Okay, so how do we get the rest of them? So the rest of the behavior that is not covered by the eigenvectors or eigenspaces rather. So once again, remember these are like planks. Okay, and the rest of them is some kind of fabric of the kind stretchy rubbery fabric. Okay, so the good news is then, just like with the standard basis, if we know where the standard bases go, okay, we know the linear operator. Remember, the matrix is made of those two. Okay, so fortunately, without referring to the matrix necessarily, but if we know where the two v1, v2 go, and we do, then we know where the rest of the vectors go, because we can express, well, that's what we see here, we can express any vector. So this is any v, let's say x, any x, it is x here, any x can be expressed as linear combination v1, v2, and therefore under linearity we also know where it goes. Okay, so that's literal computation right here. Okay, so here I'm using the linearity. First I use the definition. No, hold on. This is linearity right here. I'm using linearity here. Linearity, and then I use the eigenvalues, the fact that these are eigenvectors. So nothing but multiplication. So naturally, everything is once again the linear combination of those two vectors v1, v2, which is interesting. Okay, so that's easy. So that's kind of solving the behavior of a linear operator. Now it can be expressed in this in terms of those simplified directions. Okay, so All right, so let's quickly run through these a few examples once again. So the computation is simple enough, so you can actually establish where the linear lambda 1, lambda 2 comes from a quadratic equation. So they're right here. Okay, but then there is also slightly more algebra involved here to find the eigenvectors. But once again, it's not much of a challenge. And the as you can see here, that's what happens if we plug in our eigenvalue one at a time, into our equation, the definition of the eigenvalue, and then find x, y. Okay, so the simplification right away happens is this it turns out that the vector equation. Okay, this is my vector equation, produces two numerical equations. Okay, and so, but the good news is they are identical ones. Okay, so which means that if identical ones, then you throw one out and deal with what's left, for better or for worse, and it is actually to be expected. There are infinitely many solutions then. You are used to having an equation with a single solution, but when you have two unknowns, right, one equation, then you have infinitely many. Okay, and then that's not meaningless because there is still a relation between x and y, and specifically x is equal to y. It means that the vectors are vectors only of the form xx. Okay, so for example, 1, 1, yes. 1, 2, 1, 2, no. Okay, so that's what it means. So we do exclude infinitely many vectors. Even though we include infinitely many vectors, we also exclude infinitely many vectors. So once we look at where these vectors lie, we recognize that's the green line over there. Okay, so the components of the vector coincide and that they're all diagonal. Okay, so that's what we have found. That green line is the eigenspace. That's the eigenspace of what's the eigenvector? Eigenvector. The eigenvector is the eigenvalue is -3. So E -3. That's what we have found here. That's in green. Okay, so same story. Exactly. It is repeated for that label -2. Once again, the equation right here, -2. Once again, split it in half, component wise. Realize we have two identical equations left. Throw one out, you have infinitely many solutions, but in reality, you need only one as the direction vector of your vector and of your so this 2, 1 is yes, for example, 3, 3, no. If you want to give an example, and then what? And then you end up with a straight line that follows this vector. So this is the direction vector of the second eigenspace. So this is E -2. Okay, so once again, this is the real line, what we have found. This is E -2, while this one E -3. Okay, so once again, we not only found those lines, and really we need the vectors. We need the vectors in order for us to be able to utilize our theorem. We need the two eigenvectors, and we have them. So v1 is equal to, I picked the simplest one, right? So there are infinitely many one. The simplest one in the diagonal is 1, 1. The simplest one for the other one is 2, 1. So these are the two. And so then, as we summarize what's happening and take into consideration the actual eigenvalues. So vector 1, 1, what happens to it? It stretches by 2, but also flips. Okay, so that's what -2 means. I'm sorry, -3. So that's the -3 over here for the first eigenvalue. So 1, 1 is stretched by 3 and then flipped in the opposite direction. For the second one, the eigenvalue is -2, which means it's stretched by 2 and then flipped. Okay, so if you just look at the eigenspaces, they are intact. They look intact. So because as intended. Okay, so but if you look at actual directions, you realize that they have switched to the opposite. That's the flip, as well as maybe so if this is say like this, and this is maybe like that because it's been stretched, to the opposite. So if I do it like this, so because it's stretched now, it moves like this. Okay, in the opposite direction and stretched out. And then the rest of the part of the theorem is actually we didn't find that just the two values, even though the information is really what we're going to be using primarily is this information. This is the information we're going to be using. Nonetheless, we found the rest of the values. Okay. All right. So any questions about this example? So the experimentation is only confirmed with our analysis. So again, whatever happened to those circles. As you can see, it actually is nice. Once we know what has happened exactly, this is the description right here. What has happened right here. Stretch and flip, and then what is that we see in our experimentation that is confirmed. One thing that is confirmed is that whatever was counterclockwise is still counterclockwise because there are two flips. Okay, so these are the two flips, and so two flips brings you back to the original orientation. Okay, that's good news. So confirming our analysis by hand. With the computer, but also the stretches are not as obvious. So we know only that the stretches along the green line and along the red line are disproportional, and there is no stretching elsewhere. And so it produces a bunch of the ellipses. And look at where the way they orient. It's kind of unpredictable. So if we go to the circle, they turn into ellipses. But where does it point? Where do they point? And the answer is it's not quite clear. That's pointing like this. This is where our ellipses are pointing, and then to tell that what does it have to do with 2 and 3, and I have to say you cannot really tell if that's the question you're asking. The effect of 2 separate disproportional stretches in different directions, the effect it has on circles, say, is not something easily predict. Fortunately, we don't care about that much. The description, as I said, this is really what we care about the most. Because it's easy to translate into differential equations, which is what we are primarily after. Okay, so once again, here is the one with experimentation. Once again, the happens to be perpendicular eigenspaces, but otherwise everything is the same. So I don't think there is anything special about this. What's so special about it? So as you can see, there are 1 flip rather than 2, and then you can detect the reversal of orientation of those circles. The ellipses on the right are going clockwise, while there is nowhere counterclockwise, and there is no stretch in one of these directions. So that's all. That's why it is actually predictable. It's kind of what you want to get to do. So you say that the red line, if I draw the red line, goes towards 3 like this. Yeah. Okay. So as you can see, because there is no stretch in one of the directions, then the only visible stretch. So the stretch is visible in the direction of the red one, this one. So this stretch by 4 is visible, and only because it was invisible over here, because I tried to overlap these 2 lines over the picture on the right, and it doesn't tell you anything. Here it does, because there's only 1 stretch along one of the 2 lines. There's nothing happening along the green line, and that's why the ellipses are kind of oriented, or not kind of, definitely oriented with the red eigenspace. So otherwise, just read this. Okay, so let's summarize what we have acquired. So once again, a matrix with 2 real non-zero eigenvalues. Okay, so so they could possibly be still equal to each other. Then the function defined by that matrix, linear operator, stretches, shrinks the 2 eigenspaces by factors respectively lambda 1, lambda 2. Okay, they could be equal, and then if they have the same sign, it preserves the rotation. every closed curve around the origin has the same orientation, meaning clockwise remains clockwise. If they have opposite sides, then we have a reversal orientation. That's pretty much all there is. Reversal orientation is important because it is the exponential dynamics that we see we're going to see every time will be towards decay rather than towards growth. So that's what the negative eigenvalues stand for. Okay, one more example. This one, the sharing, once again, we already done all of that. We just want to confirm the computations that once again, this is all executed, all the numbers that we need are executed by Excel. And they, as you can see, the eigenvectors are found, happens to be 1, 0, 1. Eigenvectors is 1, 0, and 1, 0. Hold on a second. Let me see what's that we got here. So this is the case when that's a special case when the two eigenvalues are equal. So in other words, courtesy polynomial touches the x-axis like this. Okay, so this is 1 minus lambda squared. So, and this is 1. Okay. So that's a different case, and so that's what produces this particular effect. If we are now it's not covered by the classification theorem, because as you can see, the because there's only one eigenvalue, then when we carry out the same computation before, there's only one to carry out because it's the same. But turns out that nonetheless, there's only one eigenvalue, and it happens to, if you look at it, it is so there are two system of equations to be solved, but this time these two equations are not identical, but rather separate. And nonetheless, nonetheless, the second equation is dropped because y equal to 0. So the end result is still one single equation. So x plus y is equal to x. Okay, or y is equal to 0. Okay, so that is a very simple space. In other words, all the vectors in the eigenspace look like x0. Okay, so these are all horizontal vectors, which indicates that this is my eigenspace of 1. Yes. Okay, so which means that all the stretching of the only vector that is stretched and not rotated is a horizontal one. You can definitely see it here, right? So that square has become this parallelogram on the right, okay? And indeed, only the horizontal vectors under such a transformation remain horizontal. Every other vector has been rotated. All rotated, but horizontal. Okay, so that our experimentation confirms that it is indeed the case. Okay, it is a special case, and so the trouble here is then what about the rest? And it is what about the rest of vectors? And then we don't have the answer yet. So it's not covered by our theorems. About our original theorem, where we had two distinct, not distinct, but rather two eigenvectors, not multiples of each other. And here they are all the eigenvectors, of course. Okay, so that's one case. It's an edge case, but nonetheless, there's a case when the classification theorem doesn't apply. And so even though we are able to describe what's happening, but not easily express what happens to the rest of the vector. So we don't have, literally don't have the answer. The other one in a similar state is if when my characteristic polynomial one, I remember kappa. I'm sorry, not kappa, but chi of lambda. And it happens to have no roots, no real roots. So this one is still okay. This is my kappa chi of lambda. Okay, it has one single because it's a multiplicity 2 complete square, and that's why we have this special case. So if you imagine that if you are shifting the graph in the vertical direction, so sometimes either it's entirely above or partially below, And then you have case one root, two roots, 2 roots or 0 roots. And this is special transitional case from 0 to 1, from 0 to 2 is 1, and then we kind of stuck here. But this one is also stuck here with this one too, because there are no real eigenvalues, and which means that we're stuck, and so we would have to deal with a complex number. So it's plus or minus I. Okay. So what does it tell us really is unclear. So the computer doesn't care if you tell it how to do it. And after all, this comes from nothing but the quadratic formula. So if you know how to do quadratic formula, you can tell a computer how to do it. With no trouble whatsoever, and it's fine for you the eigenvectors, but not eigenvalues, but not eigenvectors. So if you can see, there is nothing here because it's not so, because there are no real eigenvectors. Okay. So anyway, unfortunately, that's one example. This 90 degrees rotation produces a very simple characteristic equation, but every single rotation has the same problem with this. I'm taking the general rotation of the triangle theta, and this is the my characteristic polynomial right here. And what is the discriminant? Okay, the discriminant is -2 squared minus 4. Hold on. I'm sorry, I lost my cosine here. -2 cosine theta minus 4. That's my discriminant. And what is it equal to? It's equal to -4 cosine theta squared theta minus 4, or -4 cosine squared theta minus 1. I'm sorry, there is no negative here. Like this. Okay. So what can you say about this expression? Cosine squared theta minus 1 equal to what? Sine squared, right? So negative sine, so a -4 sine squared theta, which is actually is totally negative. If unless theta is equal to 0, no rotation at all, then the whole number is negative, the discriminant is negative, and we do not have any real roots in, so we are stuck. Without complex numbers, we cannot continue. So then that's why we need all the background with complex numbers in order to handle these situations. So any kind of rotation is involved. So this example is actually, I'm gonna skip it. Then where you don't even know what it is, but you can detect once you run through our computations with or without experimentation, you realize that there is a characteristic polynomial has no real roots. You know that there is a rotation there. Okay, that's the rotation. It is not a rotation, but there is a rotation in there. Okay, so which means that it is informative, but we cannot be more specific about it. As you can see, there's some rotation clearly and stretching, and so but we are pretty much stuck. So we can even if we know the complex numbers, that's not sufficient. If we know complex numbers in terms of algebra, that's still not sufficient for us to solve the rest of the problems, because we would need a complex linear algebra and later on complex calculus. Pretty much that's what it is. So anyway, so with that pointed out, we concentrate on the case when we can't solve the problem. I think I could skip this and turn to differential equations. Okay, so let's quickly so we're turning towards it. So now we have even though limited to that particular case, like half, what we got is half of linear algebra we need. Okay, so that's what we have. The other half is complex. Okay, so nonetheless, let's take this half and see how far it takes us. This is what a linear differential equation looks like. So x, once again, is vector. Naturally, we stick to two-dimensional nonetheless. So A is a matrix 2 by 2, and this is the generic. No, this is non-generic. Generic looks like this. So generic case is this x, and then this is ax here. Okay, so that's generic in reference to what? X. X is location. and x prime, which is also x in the velocity. That's how we transition from linear algebra to differential equation. That's what it is. So it used to be in the abstract, one vector transformed to another vector, but really what here's a differential equation. What is it? We equate the velocity with a certain function of the location. So velocity depends, what is we're saying here, velocity depends on the location. Okay, so a flow that does not vary in time. And so if you point your finger at every point on the flow on the plane, you know which way it is going and how fast. Okay, so then what we have established is that there are special directions. So these are special now. Special directions where a of x is not turning away from x. That's the difference. See the difference here? Naturally, there is the opposite, like this. This is also possible. So ax pointing in the opposite direction. The difference is naturally, what's the difference between the two cases? So both are non-generic because a of x stretches the vector x. Okay, so what's the difference?
The sign of the eigenvalue.
The sign of the eigenvalue, correct. So lambda is positive, lambda is negative. And once again, we already predict what's going to happen. Exponential growth, case number one, exponential decay, the other one. So that's the quick preview, and now let's look at the details of what, once again, the special directions where there will be pure exponential growth or decay, even though it's not a pure population. If you have two populations, we're not speaking of one or the other, but some kind of special combination of them, which is will be exhibiting purely exponential dynamics. Okay, so linear systems of ODEs. So once again, x, y. X could be a point or it is a vector. We're using either the triangular brackets or the column notation. Okay, so the difference quotient also used once again the two notations. That's definitely a vector. And then we also we then can form this difference quotient equation, which allows us to do the modeling and the Euler solutions. Okay, and then if we take the limit, after the limit with delta t going towards zero, it's a difference quotient have derivatives. Okay, so this will be approximations. This will be exact analysis that requires the linear algebra that we have developed. Okay, so it's okay. So, all right, so this is generically, so this is non-linear necessarily. Generically, this is what that flow might look like. It's called the phase space. And once again, the best metaphor for it is this flow of a liquid on the plane. They made a very thin layer. So you're looking from above, and then everything moves in some directions, every particle. The solving the equation, you need to find a trace of something quite a bit different because you put something in the flow and see where it goes. So what does it have that it's not linear? Why do I know this is not linear? Because it changes directions all the time, and we know that that cannot happen. But there are places there around the linearization idea comes into play. If we just look at some of the points where a singular point. So this one is singular. This one is singular point. Whereas this one is singular point. So that's where f is equal to zero at those red points. So if then the idea that we have had, if we concentrate on the vicinity of that point, we will linearize. We could linearize, although we're actually not going to be doing it. But we hypothetically, with enough of calculus 3 at hand, we can. And then we, if we understand what's happening in the vicinity of every one of these special points, then we can combine things together and have a portrait of this differential equation. Okay, so once again, we're not going to be linearizing, actually doing linearization here. Assume that it's already been done. Okay, so we have a linear system so this is still non-linear necessarily. As you can see, I'm using the functional notation here f with parentheses. And when I want to emphasize the point, when we have a linear system, then what I do is I do this notation fx. Okay, so this is definitely matrix. Okay, so and that's how we can tell them apart. Okay. Okay, so once again, this is how we write the differential equation. That's the meaning of differential equation. Substitution of the function has to be a parameter curve x of t that is differentiable. It is differentiated, substituted into our equation, supposed to produce two things equal to each other. Okay, so initial value problem, uniqueness, existence. We talked about that. Euler solution is also for experimentation purposes. We're gonna do that too. And then, as you can see, it's equation exactly the same, except now we used to have these with lowercase because these were numbers, and now these are vectors. But otherwise, we can do it just the way we did it with the rest of them. Starting, we did the parent-to-prey model in exactly this manner before we actually solved it. Okay, so consecutive locations. Okay, so the technology is the same. Next location is current location plus velocity times time increment. And if these used to be numbers, now they're not, they're vectors, except for time. Time remains to be a number, but otherwise a vector is a vector. The new vector is an old vector plus the velocity vector multiplied by a number, which is time increment. So that's how Euler solutions work out. So now suppose we have linearized. Okay, suppose, and in which case we end up with a simplified equation given by four numbers. Those four numbers are combined into a matrix like this. We already did, but that before, but nonetheless, let's write it out. So x prime is a two vector, x is two vector, f is a matrix 2 by 2. Okay, so as you can see, the complexity is still there in comparison. So it used to be one number in one-dimensional case. Now it's in two-dimensional case, it's four. Okay, so the variety of things that we can examine we can encounter is will be by far higher. Okay, so the simple observation, as we know about linear operators, is that when you plug in 0 into 0, then you have 0, and those are the singular points where the flow stops. Okay, so that's what it is. It's not moving. So either everything coming out, and then these are the possibilities to consider. Either everything is going in, everything going out, some going in, some going out, and there are rotation, there are spirals. So all of these are still possibilities. We call it singular points. We call it equilibrium. We call it stationary points. All of possibilities. So once again, that's the matrix that equal to 0 when x is equal to 0. That's always that's linearity point. Okay, so a few simple examples. We already seen them, but this is the degenerate case when one of the variables do not change, y prime is equal to 0. Then, as always, when x prime is equal to 2x, with the solution that is done a while ago, it is nothing but exponential growth, CA to 2t. Now, they solved separately. We don't have to do anything, but nonetheless, just for experimentation and then visualization, this is what solution would look like. Okay, so in two-dimensional, they remain two-dimensional, even though we solve them separately. So y is not changing, and x is running away. Okay, so that's what they look like. If you zoom in, you can see that arrows are pointing away from. Okay, where am I? Pointing away. Pointing away. Where am I? Okay, so it's jump on me. Pointing away from the y-axis. Pointing away from the y-axis. So in other words, once again, two populations. One population is simply not changing, and the other one is growing exponentially, including the negative power. Okay, that's all there is. Okay, so what is so special about it? Let's recognize what it is. From the simple differential equation, we recognize what the linear operator is here, and if we just look at this matrix, it's 2, 0, 0, 0. Okay, so we know what this linear operator is. What is this linear operator with a matrix 2, 0, 0, 0?
stretch of 2 on the x-axis, and it's all projected.
And the projection of the x. So you stretch in the x direction first, and then you project on the rest of the x-axis. So it is basically a projection with a stretch, and so it is a singular linear operator, meaning what? Well, its determinant is equal to 0. And so that's why it's not 1-to-1, and so that our ability to recognize one from the other will tell us things like when the behavior is in kind of a extremely simple, okay, in this case. So we'll check that with the determinant. Okay, so once again, so if the determinant of our linear operator that defines the differential equation is not equal to 0, then there's only one equilibrium. Okay, so once again, the theorem determines, and determinant of f is equal to 0 if and only if not equal to 0, f is 1-to-1, and that's exactly it. So there are no other zeros. Being 1-to-1 means that there is no other way to get to 0 but other than 0. The 0 is always goes to 0, and therefore there will always be stationary point there, but there will be no projection. There will be development in all directions and every locations except for 0. So then once again, determinant is equal to 0, the function is 1-to-1, and therefore there's only one equilibrium. So that's the good news, and that's the primarily what we concentrate on. Otherwise, there aren't many such points. Look at it, the whole x-axis, these are stationary points. Right, so if you are at 0, if your population, hold on a second, please. Yeah, it is stationary. Yeah, if both, yeah, right, yeah, stationary. Okay. Okay, so all right, so that's a degenerate case. I just choose to start with it, but as you can see, I just want to test the determinant is the simplest tool of linearity is determinant, and it tells us a lot about what's going on. And sometimes it's not as simple as this example. We solved it first and then confirmed it with the algebra. This is that we do not know. Maybe you're not going to see right away recognize that 2, 2, 1, 2, 4, 2 is actually a singular matrix. Okay, if you do not, you do once you take the determinant. You take the determinant, you end up with a 0, and then you know that it's singular, which means that there's some kind of projection there, which means that there will be a bunch of stationary points, infinitely many stationary points, usually along that straight line. Everything projects on it, and along that straight line, there will be a lot of stationary points. So let's do that and find that particular line. In which case we know that there is somewhere. So we know that that's going to be the case. So it's a projection. So that will be the conclusion that we make. But what is that particular direction? Okay. And so without modeling, we just let's do analysis, and that analysis we already have done. So and you can detect it in a number of ways, so in this case, I jump to the conclusion that if you're not convinced, so 1, 2, if we take 2, 1, 4, 2 and multiply it by 1, 2, what do we get? We get 2 and 2 and 4. Well, 1 second. 4 and 8. Okay, which is a multiple of it is 4 of 1, 2. So that's that. I once again I skipped over of eigenvectors, so we have done this too many times. But you can get eigenvector analysis to get that answer. Turns out that 1, 2 is the eigenvector with lambda equal to 4. Okay. And then, so it means that in that direction, 1, 2, what's happening to the operator, it stretches. On the other hand, in the direction perpendicular to it, the vector is negative 1, 2, and that is the eigenvalue 0. That's what the projection is. Eigenvalue is equal to 0 gives you a projection, and which means that in that direction there will be no motion. Okay, so so if you were to carry it out, these are guesses. Or kind of a ad hoc analysis. If you want to do it straight in the, brute force, which is now amounts to brute force, you have a formula, let's do it. So my characteristic polynomial is lambda minus 4. I have two eigenvalues, 0 and 4, and once again, one will be stretched, the other one is a projection, and this is what it looks like. That's my linear operator along that line, which is 1, 2, indeed, along 1, 2, we have, no, the 1, 2 is the purple one. Okay, and that's where there's a stretching. Okay, so in this direction is a stretch, and in this direction is a collapse or projection. Okay, so all right, so what does it do to the to our differential equation? What does it do to our differential equation based on this? Well, they will always look exactly the same. So once you accept maybe rotate, so that picture will repeat itself. Okay, so every time you have a projection, your linear operator is has a projection in it, and it is the lambda is in this case once again positive, which means that there will be exponential growth away from that line. So just the line, it is not y-axis anymore. So but we have found it that red line is where nothing is changing, and so the purple lines are in fact the solutions. Okay, so these are the solutions, and they are running away. So these are solutions, and they are doing this because they are running away exponential growth. Okay, and so it debates entirely on the analysis of eigenvectors with the way to do it. Find eigenvectors at eigenvalues. Fairly straightforward, and then we have the picture. So that is the portrait of my differential equation. Once again, so all of these solutions are straight lines, and the red line is a bunch of stationary points. So, well, that's all there is really. So let's get the station. Okay. So once again, if these were two populations, you end up with some kind of complex interaction between them. Then they hurting each other, they helping each other in some complicated way. What you conclude here is that if you mix those population 2 to 1, okay, they will not be that proportion will remain the same. Okay. Yeah. The growth of two populations is always 1 to 2. Okay, so in that direction, there's nothing else. So in other words, these directions are exclusive, and there is nowhere else to go. In this degenerate non-generic case, in the generic case, there will be particular special directions. So these are not one direction. There are no other directions. So okay, so let's do that. But first, once again, classification. We already had done this: stable equilibrium, unstable equilibrium, semi-stable equilibrium. Everything is in. It is once again the words that we use is sink, source, and this one pass. Even though it's not really a pass, but some of them go in, some of them are going out. So this is once again a simple case of separating variables, which means that we can solve them separately, and once again only confirm the results that we acquire by hand by doing linear algebra. Okay, so exponential growth in these exponential decay in these directions because the number is negative over there, and then the exponential growth in these directions because the number is 4. We know already what it stands for. This lambda is equal to -1, and here lambda is equal to 4. Okay, so these are the two directions, and then once you start plotting, you combine these two pictures, which exist separately, vertical and horizontally. If you combine them together, you already can start guessing which way they're gonna the rest of the solutions will look like, right? So in the horizontal direction, for example, if I'm looking at what's happening here, I can see that we are moving on one hand, we're moving towards the y-axis. On the other hand, we're moving away from the x-axis. right? So you see it toward y-axis, away from x-axis, right? So how is it possible? Like this. Okay, so but not that actually too crude, like this. Okay, so once again, away, if this we take away from the x-axis, meaning that we're progressing vertically up, but also towards the y-axis, meaning we're decreasing the direction. So that's the one crude picture that you can produce. And then you already know that it's going to be a semi-stable equilibrium because the opposite behaviors are exhibited here. Okay. Do Euler, and it gives you exactly that very, very easily. Okay, so here I plot like 6 solutions, and here they are. So once again, if we kind of backwards look at the matrix, it is diagonal. So the computation of the is very easy, and so we solve because of the direction that in which it has been solved. Okay, so just the answer. These are two separate answers. If you were combined together, then you end up with just a linear combination of these two, right? So linear combination in the direction of x. This, and then this one is one solution. This is the other solution, and then this is a linear combination. Okay, so the two, that's the main difference from the one-dimensional case. There are two parameters. So it's a two-parameter family because we have two degrees of freedom, horizontal and vertical, and therefore the solution in the x direction and the y direction are combined together, but in an arbitrary way. Okay, so this might be bigger and this one smaller, and then and so that creates, like I said, a two-parameter family of solutions. So, so once again, it is called pass, but also it is there's another name that terms of a settle. A settle point. Remember why it's called a settle point? So, so the flows that we have seen are frequently based on a view from above, but the flow might be on the surface of on the surface. Okay, so in this case, if you have a settle point like this, and there's a flow of liquid, then it is possible that it will do this down. And then down this way. So it goes towards the origin. So this is where that's a stationary point. One point that's not moving, single point. So if you're right up there, you will going towards it, but when you get close enough to it, you turn and you go down from that settle point. So settle point or pass, in other words, for pass is in the ridge of mountains. And you're crossing between two summits, you're crossing in between, and that special point is that either you go this way up or that way you're going down. So that's what makes it special. And once again, it is on one hand, some of the water is flowing towards it, and some elsewhere flowing away from it. And that's the graphs on the right are exactly behaving like that. So it's going towards that point, and then at some point it starts to move away. Not abruptly, slowly, because everything is smooth, but nonetheless, that's the behavior, and it is to be expected. That just happens to be a diagonal matrix, but our linear algebra allows us to do everything. It doesn't matter. It makes no difference. We know how to find those special directions. So the settle point might not be necessarily like this perpendicular direction, but maybe like this. Okay, so it's slightly different, but still the idea applies. Semi-stable equilibrium. The flowing of water along a settle point that we got. Okay, so this pretty much what follows is a few examples how we look at different systems of ODEs and different behaviors they produce discovered by means of linear algebra. So this is the next one, and it's called the node, and you see why. And once again, we're looking at the simplest one. Once again, diagonal. Once again, x and y separately. Once again, you can see how they're differently they're solved with two different parameters. And then the linear combination of these two solutions will produce all the solutions. And here they are. So running away from the origin, so it's unstable equilibrium, but how it is proportional, because the x is growing slower than y. Therefore, you can see that's reflected in those curves. Okay, you can see that that it goes like this because y is growing faster. Okay, so in fact, you can guess what the curves are. Can you guess what those curves are? So this is a parametric curve, so you don't need it to do anything else. So these are the curves. But what as a function of y is a function of x? Can you see what it is? What does it look like? The curves, what do they look like? Well, if you don't see it, which is you are wise to be cautious, because naturally, if you were asked that question a few years ago, your answer would be very quickly would answer the answer they look like parabola, don't they? Don't they look like parabolas? What?
A little.
Oh, yeah. So look, it's flat here, and then it accelerates and grows. Okay, they're definitely different, and they color differently. So I'm not saying that brown and blue form one parabola. I'm saying each of these are parabolas, and they look like parabolas. And now you know better just to conclude that it's a parabola. Maybe not, probably not. But if you look carefully, then you realize that. Look at it. So if x is equal to e2t and y equal to e4t, what's the relation between x and t? Remember properties of exponents?
X squared.
X squared, right? So it is indeed e4t is in fact e2t squared, which is x squared. So these are parabolas. They all happen to be parabolas. Naturally, if the proportion was not exact as 1 to 2, they would not be. Well, first of all, if they were both 2t, then the end result would be in a straight line, right? If it is, for example, 2t and 6t, it would be a cubic curve. Okay, so which is just a nice way to notice if you pay attention. But otherwise, the solution is solved by brute force. So we plotted it by Euler brute force, but also we could have discovered all of these facts without thinking or paying attention, but just doing analysis of the eigenvalues. Okay, so the eigenvalues naturally are, well, the two numbers on diagonal probably worth mentioning. I think probably I did. So the eigenvalues of a diagonal matrix are on its diagonal. Okay, so if there are two zeros elsewhere, then the other two numbers are the eigenvalues. You don't have to do it. Okay, so linear combinations. So 3, 3 is the proportion, like I said, straight lines. When this is the matrix 3, 0, 0, 3, then the eigenvalues are equal, and everything it develops along a straight line. So it's so it's some kind of a once again a flow of a function. So this is once again a function. Okay, so this is definitely not, I'm not sure if you can you design a fountain in such a shape that the flow of water would be like this? I'm not sure. Yeah, I'm not sure it's possible. How about this one? Definitely just a conical fountain. Okay, so once again, stability of a diagonal matrix, if it is our matrix is diagonal, and well, getting ahead of ourselves, all matrices are diagonal under good circumstances. So then, so A and D, these are the two, basically, the two eigenvalues. Okay, and so when both of them are positive, then we have unstable equilibrium. Running away, if both of them are negative, we have a stable equilibrium. And if they differ in signs, that you have a semi-stable equilibrium because they're running away from each other. One runs towards and one the other away. Okay, so the difference, so that's just the two examples that we have had. Now that's just an explanation for the record of what is that we have been saying. Okay, so so what to do when the matrix is not diagonal? The answer is simple: do linear algebra. Okay, so linear algebra that has to solve, and then instead of looking at the basis vectors as you have on the left, look at the eigenvectors that now constitute the important directions, and they're like a substitute basis. Okay, so but otherwise it's the same. So once you found the eigenvectors, then the logic is the same. The two eigenvalues will determine the answers will be the same, except they will not be behaviors along the axes, but along the eigenspaces. So this one only one rotation, but there's one special direction, non-vertical, and along blue line. Apparently, it appears to be what is it? Along the y-axis there is a exponential decay. Along the blue vector, there's an exponential decay, while there's an exponential growth along the red vector. So that's what we're looking for. One eigenvalue, the other eigenvalue, one eigenvector, the other eigenvector, and then we tell what's happening, just like here, what's happening in these two directions, and then combine them together to produce the rest of the behavior. Okay, so I skewed the two pictures that we just had, these two we just had. Okay, and then I skewed them in the basically using the probably just Microsoft Paint. I skewed them to explain, to make that point, that all we need here is to look at the special vectors that we just need to know how to find them, but otherwise they are can be easily found by the linear algebra. Okay, so because the axes are incidental. Okay, so the flow flows the way it wants, and then on top of it we put our Cartesian system, and so it might not necessarily be matching the special directions. So the generic situation is on the right, and when you're lucky, you are on the left where your matrix is diagonal. Okay, so once again, this is a special situation when the two align, and so we need to find that direction, and that direction is the eigenvector. Okay, so definition of the eigenvector. To confirm that that's the case, let's just carry out this computation once to confirm that indeed not only one vector is aligned with it, but also you cannot leave this line. So if you are within the eigenspace, so this is say E lambda, you stay within it. Okay, so and that's the confirmed right here. So if x is proportional to the eigenvector with eigenvalue lambda, okay, so then this is what we have here. So you can just, what you do is you differentiate. Okay, so I take this equation. Once again, we are just taking a multiple. What is R? In other words, what we're saying here is what if x is proportional to v, but depends on time. So in other words, it was 2 and then it becomes 3 maybe. So in what way does that proportion varies. So we were speaking here of R, the stretch coefficient, which may depend on time. And I'm writing exactly that on the left what we already have here. X is equal to RB multiple of 3. What can we say about R if it possibly depend on R? And we do differentiation here. Okay, so we just take the whole equation, differentiate it, and then what you have to get, I have X prime is equal to RB prime, F of RB. I factor R out. I have R F of B, and then we would bring in the we use the linearity, then we use the definition of the eigenvalue, and then you can see what we end up with is where is it? Hold on a second. R, where is it? R prime. Where's that? Okay, this is the lambda RB. It comes from over here. Where's R prime B? Here it is. This one right here. Okay, so some of the so I do assume that you already by now have had enough experience with the parametric curves and calculus of parametric curves, and so how you differentiate it. So you don't want to go. You don't do any more components. So you just differentiate as it stands. X uppercase, its parametric curve, its input is a number, and differentiation is with respect to a number, but nonetheless, the output is a vector, and so we just write x prime. So in this case, however, R equal to RT is just a numerical function. And so when you differentiate over here, that's the where I want to point it out. So we have RB, where B is constant, but R depends on T. When you differentiate, that's what happens. So it will be still proportional to B because it's constant, and you can sort of factor it out. But then derivative of R emerges here. Okay, so because this everything is B is an eigenvector, then that's why it happened. Without being not being in an eigenvector, we would not have it. We would not have the simplification that allows us to get rid of vectors. So this is a vector equation, right? Vector equation, but because we have vector on the left and on the right is the same vector v, we can cancel it out. Okay, so we end up with a numerical equation in the next line, and so R prime is equal to lambda R, and so R is equal, and so it's solvable. So that's a dimension 1 case, and the equation is solvable. So R prime is equal to lambda R. That's the typical linear equation, right? So the answer is exponential, and lambda that used to be coefficient becomes the exponent. Okay, so we did it a few times. Once again, if you want to model its population growth, so or decay, right? So the rate of change of R, the population is proportional to the population. R prime is equal to lambda R, and so it's solved. And that's the good news, because now we can simply we know what's happening within E lambda. Okay, so if lambda is our eigenvalue, we found its eigenspace. It happens to be a straight line, then we do not leave that straight line, and within that straight line, we have exponential growth or decay with a specific formula provided. Okay, so that's the summary. So lambda is an eigenvalue, V is the corresponding eigenvector. Then the solution, we have a solution. We haven't found all the solutions, but then in that particular direction, the solution is nonetheless has been found, and it is exponential. Okay, there are no other solutions because within that eigenspace, because why? It's the easy way to explain that there are no other solutions. In one word. There is only one solution. Explaining with a single word.
Uniqueness.
Uniqueness, right? So the uniqueness, everything is differentiable. So there is uniqueness, and therefore they never do this. They are not touching. So if there's a solution there will be no crossing solution from one place to the other. So if this is our eigenspace, say lambda E lambda, then you're not gonna see anything like this. So this is a no. Or like this, hypothetically, you could draw it and it would be crossing in it tangentially, so it's possible hypothetically, but because of the uniqueness, it's not possible. That's the proof. Okay, so these are called characteristic solutions. Okay, so special solutions where the behavior is simple. So for a given eigenvector with eigenvalue lambda, E lambda TV is a characteristic solution for an eigensolution. Yeah. So that takes care of these special directions. And then once we have it, we have the other part of linear algebra that we have combining them. So once again, what you see here is two characteristic solutions. One is green, the one is red. The other one is blue. Okay, so how do you get the rest of them? We produce a linear combination of them. So some weight is given to the first, some weight is given to the second. It's literally two parameter curves, and in a way, it's like averaging. So one way probably, so I actually do it on the right in a more complex way, but one way is what is it? Literally averaging. So say R of t plus S of t 1/2 average. And in this case, in other words, it is a linear combination, right? With weights 1/2 and 1/2, which means that what is that I do? I have to pair them up appropriately. So how do I pair it? Let's say I combine this one with this one and that one. Okay, so and then I draw a straight line, and halfway that would be one of the a point on the new solution, and then I combine these two. And once again, halfway, that's the point. And then one more, there will be a point over here somewhere. Okay, so on the right, it's the same construction, slightly more complicated because the proportion is not unequal. But nonetheless, if you combine them together, that's what you got, and that's kind of a in case of semi-stable equilibrium, that's what you end up having. Something asymptotic, right? So you have asymptotic behavior on both ends. Okay, so that's we didn't discuss that a lot, but that's you can see that coming over from here and ending over there. That's the asymptotic behavior that we expect to have just by the same logic as we've seen it in when we did qualitative analysis, because it will keep going, and then where can it go as it's growing? And the answer is it will be approaching the straight line without ever crossing. And so what does that mean? It means asymptotic. So can't cross, and if it can cross, it is asymptotic. Okay, so once again, so if we have eigensolutions, two eigensolutions happen to be corresponding to eigenvectors that are not multiples of each other, okay? In which case, every solution, so we can write every solution and write them as a linear combinations. So this is example of two examples actually of linear combinations of those two solutions as simple as this. So once again, one. It looks more complicated than it deserves, but if you break it apart, you can see that there are three terms in each of them. V1, V2 are the eigenvectors, lambda 1, lambda 2 are the eigenvalues, and then C and K are once again two real coefficients creating a two-parameter family of solutions. Okay. Yeah, so once again, uniqueness, it covers the whole thing, and from the uniqueness property follows that there is nothing else. So the limitation is that the eigenvectors cannot be multiple solutions. So if it's like this, once again, remember the idea of planks and fabric between them. So if the two planks like this, and the fabric is stretched and it covers the whole plank. If they, however, they come like this, then so it does the fabric, and so it only covers one line. It does not cover the plane, and therefore some of the solutions are simply not covered, not taken care of. Okay, so, all right, so we'll do more, yeah, probably is a good place to stop, the time to stop here, so we'll do a bit more of that next time. Okay, class dismissed, see you next time.